All right. So, Chapter 3. So, what we're going to start looking at now is we're going to start looking at systems of equations. And all the different, a few things that can arise from a system of equations, and, some applications involving systems of equations, stuff like that. And the first section is relatively short. It's a pretty quick section, and it's just using the calculator to solve systems of equations and what we mean by solving a system, like the definition of that, and so on and so forth. Just a basic idea of how we solve a system. What does it mean to solve a system, and looking at a graph, a graphing calculator on how to solve it. It's pretty straightforward. So in this example right here, what we have is we have two linear models, and it's a system of two equations. And these equations measure the life expectancies in years of men and women. So when I say in years, I'm actually talking about the number of years, not, this is the age in years. That's what life expectancies measures here. Now, when it comes to solving this system, or it says right here, so this is the age expectancy of men, where T is the number of years since 1980, and this is the life expectancies of women in years since T years 1980. And we want to graph these models to predict when the life expectancies of men and women will be the same. Use your calculator. All right, so, we're just looking at, various ways we could do this in your calculator, really. That's all we're doing. So, the way you're going to do this, so let's take out your calculator, is you're going to type in those models into y equals, so go to y equals. Oh yeah, make sure that your stat plot is off again. So remember, to do that, just hit second y equals. That takes you to stat plot. Make sure your stat plot is off. Once it is, go to y equals and just type in your linear models. So 0.208x plus 69.86. Go down to y2. 0.115x plus 77.44, hit enter there. So now that they're in, just hit graph. Now when you go to graph, it's not showing up. Oh no. It doesn't mean you typed in anything wrong. It's not showing up. The graph is probably off the screen, so you just have to adjust the screen again. You just have to go to the window button. So if you look here, the window is set from -10 to 10 in the x direction and -10 to 10 in the y direction. So when you go to your graph, the graph's not showing up. Okay, so one way we could do that is we want to find the intersection point. So let's just go down to zoom fit. That might auto adjust it so that the graphs do show up. And oh, okay, that's a little better. We're actually showing up now. But we want to find the intersection point, because that's where the life expectancies of men and women will be the same when these two linear models intersect. So we're just going to adjust from this. We're going to zoom out. Once we can get the intersection point in view, we'll be good to go. So we're getting closer to it. So I could move the right arrow here to get like a better view. So now that I move my arrow over here, when I zoom out again, it's going to zoom out from this point as the center of the graph. So it'll zoom out from that point, so I'll get a better view of the intersection point. So let's zoom out. Or I meant zoom out, sorry. Enter. And now I'm getting, there's where it intersects. Good. So now I have the intersection point in view. Okay. So now I could solve this using my calculator. So the way you do that is, now that we have the intersection point in view, so the way you do this is you're going to go to second, you're going to press second, and you see right above the trace button, you see calc. You're going to press calc. That takes it to calc. When you're in the calculate, you want to go down to intersect, which is at number 5. All right, it's going to take you back to the graph. Now, what it's asking for here is it's asking for first curve. So what it's really asking for is a random point on the first curve. So you can move the arrow buttons around until you get to a random point on the curve. Now, it doesn't really matter which point you pick on the curve, but preferably you want to pick a point that's as close to the intersection point as much as possible. So that should suffice. I'm going to hit enter there. So I'll just say pick a random point on the first curve, or the first y equals. And then you're going to pick a random point on the second curve. I forgot to mention that once you pick the random point on each curve, hit enter. Just press enter. So I did that for the first curve. So the second curve, that looks good enough. I'm going to hit enter there. And then finally, it's going to ask you for guess. So you're just going to hit enter for the third time. And then that'll get you your intersect point. So I'm going to hit enter again, and boom, there's the intersection. So the intersection point, let me write it here. So the intersection point for this model is the ordered pair 81.5, comma 86.8. There it is. So that right there satisfies both equations. That's the point where both models intersect, as you can see in your calculator. All right. So what this means is that this intersection point is a solution to the system. And what we mean by that is it satisfies both equations. When you find a solution to a system of equations, the solution is going to satisfy all the equations in the system. So it's you could plug this into the function m of t and w of t in it, and you'll get 86.8. Plug in 81.5 in both of these, you're going to get 86.8 as the output. And that's true for all systems of linear equations. What we're looking at right now is a system of 2 linear equations. Yes, that means there are systems of 3 equations, 4 equations, and so on. There are systems of infinite equations, but we're definitely not looking at in this class, but yeah, they exist. So here's an example of a system with two equations. If you have two equations, you're going to have two variables, x and y. If you have three equations in a system, you're going to have three variables, and so on. So here's an example of a linear system and two equations, just like this was an example, and we actually solved it using our calculator. We're going to look at methods by hand in 3.2, but yeah, that's how you use your calculator to find it. And if we were to interpret this point, even though I don't ask you right now, but if we were to interpret this point, you should be pretty familiar with how to do that by now. This order pair represents, or this coordinate right here, 81.5, represents the number of years since 1980. So that's what, 82 years since 1980? So that's the year 2062. So in the year 2062, the life expectancies of men and women will be roughly 87 years of age. All right. Okay, so if we go on to the next page. So a solution of the system, as I already mentioned, the order pair x comma y is a solution if it satisfies both equations. Nothing complicated there. The solution set of a system is the set of all solutions of the system. So there could be multiple solutions to the system. There could be one solution, two solutions. There could be infinite solutions, as you'll see soon. So solve this system by graphing in your calculator. I know that marker kind of bled through the paper, but just ignore that. So solve the system. All right, so let's go back to our calculator. Let's get rid of those two models. And let's type in 2x plus 1 and y1, and then negative 3x plus 6 in y2. Now if I graph that, now I might have to adjust this again because the window's set up from what it was in the previous. So my default go-to window is negative 10 to 10 in the x direction, negative 10 to 10 in the y direction. It'll look much better now. Hey, look at that. So there's my intersection point. So again, second, trace, down to intersect, pick a point on the first curve, enter, pick a point on the second curve, enter, guess, enter. Intersection point. So the intersection point, using a calculator, as you can see, is the ordered pair 1, 3. So the solution set, and the way we do this, mathematically, is we use curvy brackets to denote a set. You don't have to in MLP, but that's like the technical way we do it, is the ordered pair 1, 3. So yeah, your calculator is a pretty useful tool. So yeah, nothing tricky about that. You're just typing in buttons in a calculator. Again, in the next section, we're going to solve systems by hand, but right now we're just using your calculator's features. Okay. I want to look at this note right here. Not all linear systems have one ordered pair as its solution set. Again, this had one solution. It had a single solution, 1, 3. That's the single solution. That means it satisfies both the first and second equation. Now, if I graph these two equations in my calculator. Now, if you already know what you know about slopes of lines, you could graph them and look at them that way, but if you already know what you know about slopes of lines, look at these lines here. What kind of slopes do they have? They have the same slope. What does that mean? Two lines that have the same slope are what? They're parallel. So if I graph them in my calculator, you'll see it, but these are two parallel lines. Which means what? They never intersect. So this system contains parallel lines. Which never intersect. So if the solution set is the points that intersect, and this system never intersects, then what's the solution set? Well, the solution set here is no solution. And we can actually denote that. If I use my Kirby brackets, we denote this with a 0 and a slash through it. That actually means the empty set. Which means the solution set contains no solutions. That's just a mathematical symbolic representation of empty set. So yeah, that system contains no solution because the lines never intersect. They're parallel. So yeah, a system can contain one solution. It can contain no solution. And if we go to the third page here and we solve this system, you're probably going to see another kind of system show up. So if I solve this in my calculator in this example, well, all right. If I plug, the first one's easy enough, 2x plus 1. But what's wrong with the second equation? It's not solved for y. In order to plug in my calculator, it better be solved for y. So let me solve this equation for y. Let me do it over here. So to solve this for y, you just subtract 6x from both sides. And then you're going to get negative 3y equals negative 6x minus 3. Then divide both sides by negative 3. And then you're going to get, so I could break this up, right? So negative over negative is positive. 6 over 3 is 2. So I'm going to have 2x. And negative 3 over negative 3 is positive 1. Hey, look at that. The second equation, solve for y, is this. Isn't that the same equation as the first one? It is. It's the same one as this, it's just disguised. So I have a system of equations where both equations are the same thing. So that's just graphing the same line twice. So this system contains the same equation which means that, so if this system contains two equations, then how many ordered pairs do they have in common? Well, they have, remember, a line is comprised of an infinite number of ordered pairs. So since these two equations are the same, they have all of their ordered pairs in common. So which means that they have all their ordered pairs in common. So if a line has an infinite number of ordered pairs and they have all of them in common, so that means the solution set is infinite. Hence, solution set is infinite. It just means it's infinite number of ordered pairs. Obviously, you're not going to list them all out because you'll never end. But, yeah. So, to summarize, when you're solving linear systems of equations, you have three possibilities. You have a one-solution system where the lines intersect at one point. This is number one right here. The lines will intersect at a point. Alright, we've seen a couple of those already. You have an inconsistent system. The lines are parallel. Right here. This is a one-solution system. They intersect at that point. This is an inconsistent system. They never intersect. The lines are parallel. The solution set is the empty set, which could be denoted as the zero with a slash through it. I already showed you. And this system right here is a dependent system. So this is number 2, and this is number 3. This is a dependent system where the lines are the same. So this equation was the same in both cases. So the solution set is the set of infinite numbers. In other words, this is actually two lines, but they're the same line. So they're on top of, they're superimposed basically. So it's an infinite number of ordered pairs. So the solution to this, if you go to the table, right? Let me go back to auto here. And yeah, so all of these ordered pairs, all of those ordered pairs there are the solutions to that system, which is an infinite number. Obviously, I'm not going to go through all of them, but yeah. So, yeah, when you're solving a system of linear equations, you're going to get one of three possibilities. A one-solution system, a inconsistent system which has no solution, or a dependent system which has infinite solutions. And, you know, that's really it when it comes to looking at, you know, the gist of how we solve systems of equations. Now, in this section, we only did it using your calculator, but in the next section, in 3.2, we're going to look at two methods of solving a system of equations by hand. So that's what we're going to look at next. And that's it for this section. It's pretty short. So, yeah, so that's the end of this video, and we'll look at those methods in 3.2.